For 100 years, one rule has stood above all others in physics. Nothing can travel faster than light. It is written into the foundations of how we understand reality, a cosmic speed limit that seems as unbreakable as the passage of time itself. And yet, in quiet corners of theoretical physics, in equations scribbled across whiteboards and buried inside peer-reviewed journals, something strange has been happening. A small group of physicists has been asking a question that sounds almost forbidden. What if the rule was never quite what we thought it was? What if the universe left us a loophole, hidden in plain sight, written into the very geometry of space itself? This is why a forgotten idea, once dismissed as pure science fiction, has crept back into serious laboratories and refuses to go away. Because the closer we look, the more we realize that the speed of light might not be a wall at all, but a door we simply never learned how to open. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. To understand why faster-than-light travel feels impossible, you first have to understand just how fast light really moves. Light travels at almost 300,000 kilometers every single second. In the time it takes you to blink, a beam of light could circle the entire planet more than 3 times. It is the fastest thing in existence, the absolute champion of speed in the known universe. Nothing made of matter has ever come close to matching it. The fastest spacecraft humanity has ever built, a probe sent to brush against the outer atmosphere of the Sun, reached speeds of around 600,000 kilometers per hour. That sounds astonishing, and it is. But compared to light, it is almost standing still. Light is roughly 1,800 times faster than our fastest machine. To grasp how enormous that gap is, imagine a race between the two. If our fastest spacecraft and a beam of light set off together from the Earth at the very same instant, heading toward the same distant point, the beam of light would arrive, complete its journey, and the light from its arrival would have time to travel all the way back to the starting line, while our spacecraft had barely begun to move. The machine we are so proud of, the fastest object human hands have ever launched, would be left utterly in the dust, a tortoise watching a bullet vanish over the horizon. And this is not because our engineering is crude. It is because light occupies a category entirely its own, a speed so far beyond mechanical motion that the comparison almost loses meaning. To put that gap into something you can feel, imagine you wanted to reach the nearest star beyond our own. That star system is called Alpha Centauri, and it sits about 4.24 light-years away. A light-year is the distance light travels in one full year, and it is an enormous number, nearly 9.5 trillion kilometers. So Alpha Centauri is sitting roughly 40 trillion kilometers from where you are right now. If you climbed aboard that record-breaking solar probe and pointed it straight at Alpha Centauri, the journey would take you somewhere around 7,000 years. 7,000 years. Civilizations would rise and fall before you ever arrived. Generations of travelers would be born aboard that ship, live out their entire lives, and pass away, never having known any home but the vessel itself. Their children's children's children, dozens of generations removed, might be the ones to finally glimpse the destination. A star their distant ancestors had set out toward in an age long forgotten. The people who began the journey would be ancient history to those who completed it, remembered only as names in old records, if remembered at all. This is what the distance to even the nearest star demands of us with the technology we possess today. Not a voyage, but a multi-generational undertaking, spanning more time than separates us from the dawn of agriculture. The pyramids of ancient Egypt are only about 4,500 years old, and your trip would last longer than all of recorded human history combined. And Alpha Centauri is our neighbor. It is the closest star to our sun, practically next door in cosmic terms. The galaxy we live in, the Milky Way, stretches across roughly 100,000 light-years from edge to edge. The nearest large galaxy beyond our own, Andromeda, sits about 2.5 million light-years away. At the speeds we can currently manage, reaching it would take longer than the universe has existed. When you look up at the faint smudge of the Andromeda galaxy on a dark night, the light entering your eyes left that galaxy more than 2 million years ago, when our distant ancestors were just beginning to walk upright across ancient plains. You are not seeing Andromeda as it is. You are seeing it as it was, a ghost of ancient light that has been crossing the void for longer than humanity has been human. This is the strange truth of looking into deep space. To look far away is to look far back in time, and the further we peer, the deeper into the past we see. The universe is so vast that it doubles as a kind of time machine, showing us not the present, but a layered history of light, each distant object frozen in the moment its light departed. There is something almost cruel about this when you really think it through. We can see these other worlds. We can point our telescopes at them, measure their light, detect the gases in their atmospheres, even guess at whether they might have oceans or clouds. We have cataloged thousands of planets orbiting other stars, some of them rocky and temperate, sitting at just the right distance from their suns for liquid water to exist. We know they are there. In the span of just a few decades, we have gone from knowing of no planets beyond our own solar system to confirming the existence of thousands of them, with many billions more surely waiting to be found throughout the galaxy. Some are scorching infernos, others frozen wastelands, others giant balls of gas larger than anything in our own neighborhood. But scattered among them are worlds that seem hauntingly familiar, rocky planets of roughly the right size, orbiting their stars at roughly the right distance, where temperatures might allow liquid water to pool on the surface, where the basic conditions for life, as we understand it, might be met. We can almost taste the possibility of standing on their surfaces, of feeling an alien wind, of looking up at a sky scattered with unfamiliar constellations. And yet, every one of those worlds is locked away behind a barrier of distance so vast that, with the tools we have today, they might as well be painted onto the inside of a dome we can never touch. This is the great frustration of the cosmic age. We have learned enough to know what lies out there, but not nearly enough to go and see it for ourselves. We are like sailors who have spotted distant islands on the horizon, only to discover that no ship we can build will ever cross the ocean between. For some thinkers, this realization breeds a kind of cosmic loneliness. We may be surrounded by countless worlds, and yet so utterly isolated by distance that we can never reach a single one of them. It is a peculiar kind of solitude to be encircled by destinations and unable to visit any of them, to know that the universe is vast and full and yet feel trapped on a single grain of sand within it. This is the problem that haunts every dream of exploring the stars. Space is not just big. It is so unimaginably vast that the rules of physics seem to mock us at every turn. And the cruelest part of all is that the universe appears to have set a hard limit on how fast anyone can ever go. That limit is the speed of light. And to understand why it exists, we have to travel back a little more than a century to the mind of a young patent clerk in Switzerland. In the early 1900s, a man named Albert Einstein was working an ordinary job, reviewing patent applications, while his real passion lived in the strange world of physics. He was not, at this point, a famous professor surrounded by admirers and resources. He was a young man with a modest position, examining the designs of inventors, stamping documents, doing the unremarkable work that paid his bills. But in the quiet hours, in his own mind, He was wrestling with questions that the greatest scientists of the age had failed to answer. There is something deeply human and inspiring in this picture. The revolution that would overturn 3 centuries of physics did not begin in a grand laboratory or a prestigious university. It began in the imagination of an ordinary clerk who simply refused to stop asking why. He kept circling back to a single, troubling puzzle about light. Other scientists had measured the speed of light with great precision, and something about the results simply did not make sense. No matter how you moved, no matter how fast you chased after a beam of light or ran away from it, the light always seemed to travel at exactly the same speed relative to you. This should be impossible. Think about driving down a highway. If you are moving at 100 kilometers per hour and another car passes you, going 120, that other car only appears to pull away from you at 20 kilometers per hour. Speeds add and subtract in a way that feels obvious and natural. But light refused to play by these rules. Whether you raced toward a beam or fled from it, the beam always approached you at the same fixed speed. Imagine standing on a train platform as a train roars past at incredible speed. Someone on that train shines a flashlight forward, in the direction the train is moving. Common sense says that the light from that flashlight should be moving faster from your point of view, because the speed of the train should add to the speed of the light, but it does not. You would measure that light traveling at exactly the same speed as if the train were standing perfectly still. The motion of the train adds nothing at all. This result had been confirmed by careful experiments, and it made no sense within the comfortable world of ordinary physics. It was as if the universe had quietly decided that the speed of light was sacred, a fixed feature of reality that nothing could alter, no matter how you moved or how hard you tried. Einstein, almost alone among his peers, refused to look away from this strangeness. Instead of treating it as a puzzle to be explained away, he treated it as a clue, a window into a deeper truth about how reality is built. He decided to take the constancy of light speed, not as a problem to be solved, but as a fundamental law of nature, and to follow that law wherever it led him, no matter how bizarre the destination. Einstein realized that if the speed of light truly never changed, then something else had to give. And the things that gave way were the 2 things we trust most deeply: space and time. Think about how absolute these 2 things feel to us. A second is a second, we assume, ticking by at the same steady rate for everyone, everywhere, throughout all of existence. A meter is a meter, a fixed and unchanging length, the same whether you are standing still or racing across the world. These seem like the most solid, dependable features of reality, the unshakable foundation on which everything else is built. Einstein's astonishing insight was that they are not absolute at all. Time can stretch and compress. Space can shrink and expand. What one observer measures as a second, another, moving differently, might measure as something longer or shorter. The steady, universal flow of time that we feel so certain of is an illusion born of our slow, earthbound lives. In the wider universe, time and space bend and flex, and the only thing that stays truly constant is the speed of light itself. His conclusion, which became known as the theory of special relativity, rewrote the foundations of reality. If the speed of light is always constant for everyone, then time itself must slow down for objects moving very fast. Distances must shrink. The faster you move through space, the slower you move through time. This sounds like fantasy, but it is one of the most real things we know. Consider what happens to a particle called a muon, born high in the atmosphere when cosmic rays slam into the air far above our heads. These muons are unstable, and they decay so quickly that, by all rights, they should vanish long before they ever reach the ground. The distance is simply too great for them to survive the trip at the speeds they travel. And yet, they do reach the ground, in enormous numbers, detected by instruments at sea level every single day. The reason is time dilation. Because the muons are moving so close to the speed of light, their internal clocks run slow from our perspective. What feels like an instant to the muon stretches into enough time, from our point of view, for it to complete its journey to the surface. The muon does not experience any of this as strange. From its own perspective, time runs perfectly normally, but the distance to the ground appears dramatically shortened, squeezed down by the very same effect seen from the other side. Both views are correct. Both are real. Neither the muon nor the observer on the ground is mistaken. They simply inhabit different perspectives, each valid, each describing the same events through the lens of their own motion. This is the heart of relativity, that space and time are not the rigid, universal backdrop we always assumed, but flexible quantities that shift depending on how you move. The muon experiment is not some obscure curiosity confined to a single laboratory. These particles rain down on us constantly, all over the world, and detectors everywhere confirm the same astonishing result. The numbers match Einstein's predictions with breathtaking precision. If time did not slow for the fast-moving muons, they would decay long before reaching the ground, and detectors at the surface would catch almost none of them. Instead, they arrive in abundance, exactly as relativity predicts, a daily and unmistakable demonstration that time itself bends to the dictates of motion. This is not a trick of perception or a flaw in our instruments. It is the actual structure of the universe. It has been confirmed countless times. Clocks flown on fast aircraft tick slightly slower than identical clocks left on the ground. The satellites that power navigation systems have to constantly correct for the fact that time runs at a slightly different rate up there in orbit. Consider what that really means. The system that guides you to a destination, sitting in millions of pockets and dashboards around the world, depends on a fleet of satellites orbiting high above the Earth. Those satellites carry extraordinarily precise clocks. And because they are moving fast and sitting higher in the Earth's gravity, their clocks tick at a subtly different rate than the clocks on the ground. If engineers ignored this difference, if they treated time as the simple, universal thing our intuition imagines, the navigation system would drift off course almost immediately, accumulating errors that would grow with every passing hour until it became useless. The only reason it works at all is that the engineers build Einstein's strange truths directly into the calculations. Every time you find your way using one of these systems, you are relying on the reality of relativity, on the fact that space and time genuinely bend and flow in the ways Einstein described. It is not an abstract theory locked away in textbooks. It is woven into the everyday machinery of modern life. Relativity is not a guess. It is one of the most thoroughly tested ideas in all of science. And tucked inside this beautiful, strange theory is the speed limit that seems to crush all hope of reaching the stars. As any object with mass speeds up, it becomes harder and harder to accelerate further. The closer you push toward the speed of light, the more energy it takes to go just a little bit faster. To reach the speed of light exactly, you would need an infinite amount of energy. Infinite, a number so large it does not really exist in any practical sense. It is not merely a very big number. It is a number beyond all numbers, a quantity that can never be gathered, never be supplied, never be reached, no matter how long you labor or how much you build. This is why physicists say that nothing with mass can ever reach the speed of light, let alone surpass it. It is not that our engines are too weak or our fuel is too poor. It is that the universe itself raises the toll higher and higher until the price becomes impossible to pay. There is a deep reason for this, hidden in one of the most famous equations ever written. Energy and mass, Einstein showed, are two faces of the same thing. A small amount of mass contains a staggering amount of energy locked inside it, which is precisely why the sun can shine for billions of years and why nuclear reactions release such enormous power. But this relationship cuts both ways. When you pour energy into an object to speed it up, that energy does not simply vanish into motion. Some of it effectively adds to the object's mass, making it heavier and therefore even harder to accelerate. The faster you push, the more massive the object becomes, and the more massive it becomes, the more energy you need to push it just a little faster. It is a trap that tightens the closer you get to the speed of light. Near that limit, an object behaves as if its mass is ballooning toward infinity, and no engine, no matter how powerful, could ever supply enough energy to finish the job. This is why the speed of light is not just a practical difficulty, but a fundamental barrier. It is woven into the deepest relationship between energy, mass, and motion. For most of the 20th century, that was the end of the conversation. The stars were locked away behind a wall no machine could ever climb. If you wanted to visit another star system, you would have to accept journeys lasting thousands of years, generation ships where great-grandchildren would arrive at destinations their ancestors had only dreamed of. But here is where the story takes a turn that almost nobody expected, because Einstein's theory has two parts. The first part, special relativity, deals with motion and sets that famous speed limit. But Einstein was not finished. He spent another decade wrestling with an even deeper question, and the answer he found would crack the door open to something extraordinary. That second part is called general relativity, and it is a theory about gravity, but it is also, secretly, a theory about the shape of space itself. Before Einstein, people imagined gravity as an invisible force, a kind of cosmic rope reaching out from the sun to grab the planets and hold them in their orbits. Einstein saw something far stranger and far more elegant. He realized that space is not an empty, rigid stage on which events simply happen. Space is flexible. It can stretch, bend, ripple, and curve. And what we feel as gravity is nothing more than the curving of space around massive objects. Imagine a heavy bowling ball placed in the center of a stretched rubber sheet. The ball sinks down and creates a dip, a curve in the surface. Now roll a small marble across that sheet, and it will spiral inward toward the ball. Not because the ball is pulling it with some invisible rope, but simply because the surface it travels across is curved. The marble is doing the most natural thing in the world, following the shape of the surface beneath it. There is no force reaching out to grab it. There is only the curve, and the marble obediently rolling along that curve. This was Einstein's radical reimagining of gravity. What Isaac Newton had described as a mysterious force acting across empty space, Einstein revealed as something far more concrete and far more beautiful. Gravity is geometry. It is the shape of space, and objects move the way they do simply because they are following the contours of a landscape we cannot see. This is how Einstein described gravity. The sun bends the space around it, and the planets roll along those curves, like marbles, following the contours of a valley. But it goes deeper than just space. Einstein showed that space and time are not separate things at all, but woven together into a single fabric, something physicists call spacetime. When a massive object curves this fabric, it bends not only space but the flow of time itself. This is why clocks tick slightly slower near a massive body than they do far away from it. Closer to the Earth, time runs marginally slower than it does high up in orbit. an effect so real that the satellites guiding cars and phones must constantly account for it, or their calculations would drift hopelessly off course. Gravity, then, is not a force pulling on objects from a distance. It is the shape of space-time, and everything simply follows the contours of that shape, like water flowing downhill. A planet orbiting the sun is not being tugged by an invisible rope. It is gliding along the straightest possible path through a region of space-time that the sun has bent into a curve. This idea was not just poetic. It made predictions that turned out to be astonishingly accurate. It predicted that light passing near the sun would bend slightly as it crossed the curved space, and astronomers confirmed it during a solar eclipse. It predicted that massive objects could warp space so severely that not even light could escape, and we now know those objects as black holes. It predicted that space could carry ripples, waves spreading outward when massive bodies collide. And a century later, we built detectors sensitive enough to feel those ripples wash over the Earth. That last prediction deserves a moment of awe. When two black holes, each many times more massive than the sun, spiral into one another and merge in the depths of space, the violence of that collision sends waves rippling outward through the fabric of space-time itself. These are not waves in any substance, not in air or water, but waves in the geometry of reality, stretching and squeezing space as they pass. By the time such a wave reaches the Earth, after traveling for perhaps 1 billion years across the cosmos, it has faded to something almost unimaginably faint, distorting space by less than the width of a single atom across the span of an entire detector. And yet, we built instruments delicate enough to catch them. We have now felt the trembling of space-time from collisions that happened before complex life existed on Earth, confirming in the most dramatic way possible that space is exactly the flexible, dynamic thing Einstein said it was. Every one of these confirmations matters enormously for our story, because each one tells us the same thing. Space is not a fixed and rigid stage. It bends. It stretches. It ripples. It is a living, malleable thing, and anything malleable can, in principle, be shaped. General relativity passed every test we threw at it. And once you accept that space can stretch and bend, a remarkable possibility opens up. If space is flexible, then perhaps it can be reshaped. And if it can be reshaped, then maybe, just maybe, the cosmic speed limit is not as absolute as it first appears. Because here is the subtle, beautiful loophole hidden inside Einstein's work. The speed limit applies to objects moving through space. It does not apply to space itself. Space, it turns out, can do whatever it likes. This distinction is everything, and it is easy to miss. The famous rule, the one that says nothing can exceed the speed of light, is really a statement about how things move from one point of space to another. A ship firing its engines, a particle racing through a collider, a beam of light crossing a room. All of these are objects traveling through space, and all of them are bound by the cosmic speed limit. But space itself is not an object moving through anything. It is the stage, not an actor upon it. And the stage is under no obligation to obey the rules that constrain the actors. Space can expand, contract, stretch, and warp at any rate it pleases, including rates that would carry objects embedded within it apart faster than light could ever travel between them. The speed limit never applied to space. It only ever applied to motion through space. And in that gap, in that overlooked distinction, lies the entire hope of reaching the stars. We already have proof of this, and the proof is written across the entire sky. When astronomers look out at distant galaxies, they find that almost all of them are rushing away from us. The further away a galaxy is, the faster it appears to be receding. This is the expansion of the universe, the lingering aftermath of the moment everything began. The entire cosmos is growing, stretching ever larger as the space between galaxies swells. And here is the part that should make you sit up. The most distant galaxies are receding from us faster than the speed of light. Let that sink in. There are regions of the universe so far away that the space between us and them is expanding so quickly that their light will never reach us. They are, in a very real sense, moving away faster than light can travel. But this does not break Einstein's rule. Those galaxies are not racing through space faster than light. They are sitting more or less still in their own little patch of the cosmos. It is the space between us that is stretching, carrying them away. To picture this, imagine a loaf of raisin bread dough, with raisins scattered throughout it, sitting in a warm oven and slowly rising. As the dough expands, every raisin moves away from every other raisin. But no single raisin is actually crawling through the dough. They are all sitting still, embedded in the dough, while the dough itself swells between them. A raisin near the edge, far from a chosen central raisin, will appear to recede very quickly indeed, simply because there is so much expanding dough between them. The raisins on the far side are not breaking any rule of how fast a raisin can move. They are being carried apart by the swelling of the dough itself. The galaxies of our universe are exactly like those raisins, and the dough is space. Distant galaxies recede not because they are flying through the cosmos at incredible speed, but because the space between us and them is constantly being created, swelling outward in every direction at once. The further away a galaxy is, the more expanding space lies between us, and so the faster it appears to flee. Beyond a certain distance, that swelling adds up to a recession faster than light. Even though no galaxy is actually moving through its own local space at anything close to that speed. No rule is broken, because the speed limit was only ever about movement through space, not the expansion of space itself. And this is the crack in the wall. This is the door physicists notice standing slightly ajar. If the universe can stretch space to carry galaxies away faster than light, then in principle, space can be manipulated. The question that haunted a small number of theorists was simple to ask and fiendishly hard to answer. Could we learn to manipulate space ourselves? The universe clearly knows how to do it. It stretches space on the grandest scales imaginable, swelling the cosmos and carrying galaxies apart faster than light without the slightest difficulty. In the earliest instance after the universe began, space expanded at a rate so staggering that the entire observable cosmos ballooned from something smaller than an atom to something enormous in the tiniest fraction of a second. If nature can do this, the theorists wondered, then the bending and stretching of space is not forbidden by any law. It is simply a matter of having the means to do it. The universe does it with the raw energies of creation itself. The question was whether we, with our far humbler resources, could ever learn to do it on a smaller, more controlled scale. Could we build something that stretches and squeezes the fabric of reality, carrying a ship across the cosmos faster than light, without that ship ever breaking the speed limit inside its own little bubble of space? For decades, this was nothing more than a dreamy thought experiment whispered among physicists. Then, in the early 1990s, a Mexican theoretical physicist named Miguel Alcubierre decided to take the dream seriously and run the mathematics. The story of how he came to it has a charming honesty to it. He had grown up loving science fiction, fascinated by the idea of ships that could leap between stars in the blink of an eye. As he became a serious physicist, steeped in the rigorous mathematics of general relativity, That childhood fascination never quite left him. One day, he found himself wondering whether the warp drives of his favorite stories could be more than fantasy, whether the flexible nature of space that Einstein had revealed might actually permit something like them. Rather than dismiss the idea, as so many would have, he sat down and worked through the equations to find out. What he discovered would electrify the world of theoretical physics and put the phrase warp drive, once the property of science fiction, into the pages of serious scientific journals. Alcubierre asked himself a precise question. Using the actual equations of general relativity, could you write down a configuration of space that would carry a ship faster than light? Not a vague hand wave, but a real solution, mathematically consistent with everything Einstein had laid down. And the answer, to the astonishment of many, was yes. It is worth dwelling on just how surprising this was. For most physicists, faster-than-light travel was not merely difficult, it was a closed case, a settled impossibility filed away alongside perpetual motion machines and other discredited dreams. To suggest otherwise was to invite ridicule. And yet here was a solution, derived not from wishful thinking but from the very same equations that every physicist trusted. The equations that had passed every test, that governed black holes and the expansion of the universe and the bending of starlight. Those trusted equations, when pushed in an unexpected direction, did not slam the door on faster-than-light travel. They quietly opened it. This is one of the most remarkable things about mathematics and physics. Sometimes the equations know more than the people who write them. Sometimes a theory, built to explain one set of phenomena, turns out to permit possibilities its creators never imagined. Einstein built general relativity to explain gravity. He never set out to design a warp drive. But the structure he created was richer than he knew, and hidden within it, waiting to be discovered, was a blueprint for moving faster than light. His idea was elegant. Imagine a spacecraft sitting inside a small bubble of flat, ordinary space. Inside this bubble, everything is calm and normal. If you were aboard the ship, you would feel no acceleration, no crushing forces, no sense of motion at all. You could be sipping a drink while the stars streamed past faster than light outside your window. There is something almost paradoxical about this calm interior. In every other vision of high-speed travel, speed comes with violence. Rockets crush their passengers with acceleration. Approaching the speed of light through ordinary space brings the strange distortions of time and the punishing energy demands we have already explored. But inside the warp bubble, none of that applies. The ship and its passengers are not accelerating at all in the conventional sense. They sit in a quiet pocket of flat, undisturbed space, as still and peaceful as if they were parked in empty space, far from any star. All the motion, all the drama, all the bending of reality happens outside the bubble, in the reshaped space that surrounds it. The passengers would feel nothing. No force pressing them into their seats. No sense of tremendous velocity. Just the stars sliding past the windows at impossible speed, while inside, everything remained utterly serene. The trick was in what happened to the space around the bubble. In front of the ship, space would be compressed, squeezed and contracted, pulling the destination closer. Behind the ship, space would be stretched and expanded, pushing the point of origin further away. It helps to picture this carefully, because it is the heart of the whole idea. Imagine you are standing at one end of an enormously long carpet, with your destination at the far end. Normally, to reach it, you would have to walk the entire length of the carpet, step by exhausting step. But now imagine you could reach out and gather the carpet in front of you, bunching it up, folding it toward yourself so that the far end was drawn close. At the same time, behind you, the carpet you had already crossed would unfurl and stretch away into the distance. You would not have to walk at all. By gathering the space ahead and releasing the space behind, the destination would simply come to you, while the place you started from receded far away. This is precisely what the warp bubble does, except the carpet is the fabric of space itself, and the gathering and unfurling is the compression and expansion of spacetime. The bubble of normal space, with the ship inside it, would ride this wave of compressing and expanding space like a surfer riding a wave across the ocean. The surfer is not swimming faster than the water. The wave carries them. A surfer paddling with their arms could never hope to match the speed of a powerful ocean wave, but they do not need to. They simply position themselves on the moving wall of water and let it carry them forward, gliding effortlessly at a speed their own muscles could never produce. The energy comes from the wave, not from the surfer, and so the surfer arrives at the shore far faster than they could ever swim. This is the crucial point, the one that unlocks everything. The source of the speed is external. It does not come from the traveler straining against the limits of their own motion, but from the movement of something far larger, which the traveler simply rides. This is the heart of the warp idea. The ship does not provide the speed. The reshaping of space provides the speed, and the ship merely rides it. In exactly the same way, the ship would never move faster than light through its own local space. It would simply be carried along as space itself was reshaped around it. The destination would rush toward the ship as the space in front collapsed, and the origin would fall away as the space behind expanded. To an outside observer, the ship would appear to travel faster than light. But inside the bubble, the laws of physics would remain perfectly intact, no rule broken. No infinite energy required to push a massive object to impossible speeds. The ship is not pushed at all. The universe carries it. This is the genius of the idea, and it is worth letting it settle fully. The reason ordinary faster-than-light travel is impossible is that you would have to accelerate a massive object up through the speed of light, which demands infinite energy. But the warp ship never accelerates in that way. It never tries to push itself through space faster and faster. Inside its bubble, it barely moves at all relative to the space immediately around it. All the speed comes from the reshaping of space outside the bubble. The ship sidesteps the entire problem. It does not climb the impossible mountain of infinite energy because it never attempts the climb in the first place. It simply lets the landscape of space rearrange itself, bringing the destination near while it sits quietly in its pocket of calm. This is why the idea cannot be dismissed as a mere violation of known physics. It does not violate anything. It threads the needle, finding the one path through Einstein's equations that reaches the stars without breaking a single law. This became known as the Alcubierre drive, and when the mathematics was published, it landed like a thunderclap. For the first time, faster-than-light travel was not just a fantasy. It was a genuine, mathematically valid solution to the equations that govern reality. Word of the result spread quickly through the physics community. Some greeted it with delight, thrilled that the dream of the stars had found a foothold in serious science. Others were more cautious, quick to point out the enormous obstacles that stood in the way, the impossible energies and exotic ingredients the design seemed to require. But whatever their reaction, no one could simply dismiss it. The mathematics was sound. It did not break any known law of physics. It used the trusted equations of general relativity exactly as they were written, and it arrived at a conclusion that had been considered impossible for the better part of a century. That alone made it impossible to ignore. A serious, peer-reviewed result now existed, showing that, in principle, the universe permitted travel faster than light. The conversation had changed forever. The dream of reaching the stars within a human lifetime suddenly had a foothold in real physics. But before anyone started building starships, the same mathematics that gave us hope also delivered a brutal catalog of problems. And these were not small problems. They were the kind of obstacles that made many physicists wonder whether the whole idea was, in the end, impossible after all. The first and most serious problem was energy. To bend space in the way Alcubierre described, you do not just need a lot of energy. You need a very particular and very strange kind of energy. To compress space in front of the ship is something the universe knows how to do. Massive objects do it all the time. But to expand space behind the ship, to push it outward, you need something that behaves in the opposite way to ordinary matter. You need what physicists call negative energy. Ordinary matter and ordinary energy curve space in one direction, pulling things together. To create the stretching part of the warp bubble, you would need something that curves space the other way, pushing things apart. This exotic substance is sometimes called negative energy, and it is one of the strangest ideas in all of physics. To grasp how peculiar it is, think about how ordinary matter behaves. Everything you have ever touched, every star, every planet, every atom in your body, gravitates. It pulls. Mass and energy, in the everyday world, always bend space inward, always draw things together. Negative energy would do the opposite. It would push space apart, repel rather than attract, behave in a way that runs against everything our intuition tells us matter should do. It is the cosmic equivalent of a debt, a region where there is somehow less than nothing, less energy than the empty vacuum itself contains. The very phrase sounds like a contradiction. How can there be less than empty? How can you have a hole in the fabric of nothing? The trouble is that we have almost never seen it. In everyday life, energy is always positive. A cup of coffee has energy. A moving car has energy. A battery has energy. You cannot simply have less than nothing. Everything in your experience, every object, every process, every flicker of heat or motion carries a positive amount of energy. The very idea of negative energy runs against the deepest grain of common sense. It is like being asked to imagine a hill that is lower than flat ground, a debt of energy owed to the universe, a region scooped out below the level of true emptiness. Nothing in ordinary life prepares us for such a concept, and yet, the equations of warp travel demand exactly that. For a long time, many assumed negative energy was pure fantasy, a mathematical phantom with no place in reality. But here is where things get interesting, because negative energy is not entirely fictional. There is a phenomenon in quantum physics that hints it might be real. It is called the Casimir effect, and it was predicted by a Dutch physicist in the late 1940s. To understand it, you have to abandon the comfortable idea that empty space is truly empty. According to quantum physics, the vacuum of space is not a calm, lifeless void. It is a seething, restless sea of energy, where tiny particles flicker in and out of existence faster than we can ever catch them. This is one of the most counterintuitive discoveries in all of science. We tend to think of empty space as the ultimate nothing, a perfect blankness containing absolutely no thing at all. But the deeper physicists looked, the more they realized that this picture is wrong. At the smallest scales, the vacuum churns and boils with activity. Pairs of particles spring into being, borrowing energy from the vacuum itself, existing for the briefest flicker of time, and then vanishing again before they can be directly seen. This constant, frantic creation and destruction is happening everywhere, all the time, in every cubic centimeter of so-called empty space, including the space inside your own body and the space between the stars. The emptiest void you can imagine is in fact alive with this hidden quantum activity. It is the true nature of nothing, and it turns out that nothing is far busier than anyone ever suspected. Even in the emptiest possible region, far from any star or planet, this quantum activity hums away constantly. Now imagine placing two flat metal plates extremely close together in this vacuum, almost touching, separated by a distance smaller than a hair. Certain forms of this quantum activity cannot fit in the narrow gap between the plates, while outside the plates, the full range of activity continues unrestricted. The result is that the region between the plates contains less energy than the region outside. And less than the normal vacuum means, in effect, negative energy. The plates are gently pushed together by this difference, and that push has been measured in real laboratories. The first time this was confirmed, it was a quiet triumph of physics, a demonstration that the restless energy of the vacuum was not just a theoretical abstraction, but something with real, measurable consequences in the physical world. Two ordinary metal plates, brought close enough together, feel a genuine force arising from nothing more than the structure of empty space between them. It is one of the most striking confirmations that the vacuum is alive with hidden activity, and that this activity can be coaxed into producing the strange condition of less than nothing. The Casimir effect is real. It has been confirmed by experiment. When physicists first measured the tiny force pushing those plates together, they were touching the strange quantum underpinnings of reality itself. The force is incredibly faint, far too weak to notice in everyday life, but in the delicate world of microscopic measurements, it is unmistakable. What it reveals is profound. It tells us that the vacuum is not empty, that it possesses a structure and an energy of its own, and that by arranging matter cleverly, we can reach into that vacuum and lower its energy below the normal level. We can, in effect, create small pockets where the energy is negative compared to the surrounding emptiness. This is the closest thing we have to a real, laboratory-confirmed example of the exotic ingredient that warp travel seems to require. So negative energy, the very thing a warp drive seems to require, is not pure science fiction after all. It exists, at least in tiny, fleeting amounts, in the strange quantum corners of reality. But there is a vast gulf between detecting a microscopic effect between two plates and powering a starship across the galaxy. When Alcubierre's original design was studied, the amount of negative energy it required was almost beyond comprehension. The early calculations suggested you would need an amount of energy comparable to the entire mass of a giant planet, perhaps even more, all of it converted into this exotic negative form. Some estimates were even worse, suggesting you would need more energy than exists in the entire observable universe. Stop and consider the absurdity of that. The observable universe contains hundreds of billions of galaxies, each holding hundreds of billions of stars, every one of them a furnace, pouring out energy on a scale beyond comprehension. To suggest that a single warp journey might require more energy than all of that combined is to push the idea past the boundaries of any conceivable engineering. It would be like being told that to light a single candle, you would first need to harness the output of every fire that has ever burned in the history of existence. Numbers like these are not just discouraging. They seem to slam the door shut completely. It is one thing to have a clever loophole in the equations. It is another thing entirely to need more energy than all the stars in the cosmos could ever provide. For years, this seemed to be the final word. The Alcubierre drive was a beautiful idea, mathematically valid, but utterly impractical. A fascinating curiosity, nothing more. To understand just how daunting these numbers were, it helps to picture what converting a planet's worth of mass into pure energy would actually mean. The energy locked inside even a small amount of matter is colossal. The entire arsenal of every weapon humanity has ever built represents only the tiniest sliver of the energy contained in a single mountain. Now imagine needing the full energy equivalent of an entire giant planet, a world larger than anything in our solar system, and then imagine needing it in the exotic negative form that we can barely produce at all. The mismatch between what the theory demanded and what we could ever hope to provide was so enormous that it bordered on absurd. It was like being told that the recipe for crossing the galaxy required an ingredient that did not exist in usable quantities, measured in amounts beyond all imagining. For anyone hoping to build a real starship, it was the bleakest possible news. And yet, the story did not end there. Because once an idea is shown to be possible in principle, clever minds begin to chip away at the impossible parts. If the original design needed the energy of a planet, perhaps a smarter design would need less. This is exactly what began to happen. A new generation of physicists looked again at Alcubierre's equations and asked whether the staggering energy requirement was truly fundamental, or simply a feature of his particular design. This is how science often advances, not through a single dramatic breakthrough, but through patient re-examination, through asking whether the obstacles everyone has accepted are really as solid as they seem. The first warp design was never meant to be the final word. It was a proof that the thing was possible at all. A rough first sketch, and like any first sketch, it was crude and wasteful. The physicists who followed treated it not as a finished blueprint, but as a starting point, a thing to be refined, optimized, and improved. They asked the questions that good engineers always ask. Where is all this energy actually going? Which features of the design are essential, and which are merely accidents of how it was first written down? Could a cleverer arrangement achieve the same result for far less? Maybe, they reasoned, there were other shapes for the warp bubble, other configurations of space that would do the same job for a fraction of the cost. One important breakthrough came when researchers realized that the thickness of the bubble wall mattered enormously. In the original design, the boundary of the warp bubble, the region where space transitions from compressed to expanded, was infinitely thin. This razor-sharp edge was part of what made the energy demands so monstrous. By making the walls of the bubble thicker and gentler, the energy requirement dropped dramatically. Not by a little, but by many, many orders of magnitude. The reason for this is subtle but important. Where space had to transition abruptly from compressed to expanded, the curvature became violent, almost infinitely sharp, and sharp curvature in space-time is extraordinarily expensive in terms of energy. It is a little like the difference between bending a sheet of metal gently over a wide curve versus trying to fold it into a razor-sharp crease. The gentle bend costs almost nothing. The sharp crease demands enormous force and can tear the material apart. In the original warp design, the boundary of the bubble was the equivalent of that razor-sharp crease, and the cost of maintaining it was monstrous. By softening the transition, spreading the curvature out over a thicker, gentler region, the energy demand collapsed. This single insight transformed the problem from utterly hopeless into merely staggering, and in the world of theoretical physics, that is a meaningful kind of progress. Suddenly, the planet-sized energy budget shrank towards something merely enormous instead of utterly impossible. Then came another insight. What if the bubble did not need to be large? A smaller warp bubble, just big enough to carry a modest craft, would require far less energy than one large enough to enclose a city. There is a certain irony in this realization. The grand vision of warp travel had always imagined vast starships, enormous vessels carrying hundreds of passengers between the stars. But the mathematics suggested that the smaller and more modest the bubble, the cheaper it became to create and sustain. A tiny bubble, carrying perhaps just a small probe or a single chamber, might one day lie within reach, long before a great passenger liner could be contemplated. The first warp journeys, if they ever happen, might be made not by crowds of explorers, but by humble robotic scouts, slipping quietly across the void to send back the first images of another star seen up close. Step by step, design by design, the theoretical price of a warp drive kept falling. It was still far beyond anything we could build today. But the trend was unmistakable and deeply encouraging. The energy requirement was not a fixed, unbreakable wall. It was a problem of engineering and cleverness, and clever people kept finding ways to bring the cost down. And then, in recent years, the story took its most dramatic turn yet. A group of physicists asked a question that almost nobody had dared to ask before. Did a warp drive really need negative energy at all? For decades, the requirement for exotic negative energy had been treated as an unbreakable law of warp travel. It was assumed that any faster-than-light bubble would demand this strange and possibly impossible substance. But assumptions, in physics, are meant to be tested. And when these researchers dug into the mathematics with fresh eyes, they began to suspect that the assumption was not as solid as everyone believed. In the early 2020s, a series of papers appeared that sent a ripple of excitement through the small community of physicists who study these ideas. These papers claimed something remarkable. It might be possible, they argued, to design a warp bubble using only ordinary positive energy. No exotic negative energy required at all. If true, this would be a monumental shift. The single greatest obstacle to warp travel, the need for a substance we are not even sure can exist in large amounts, might simply vanish. To understand why this mattered so much, you have to remember that the negative energy requirement had hung over the entire field like a death sentence. It was the one obstacle that seemed truly fundamental, not just a question of building bigger machines or finding more fuel, but a demand for a kind of matter that might be forbidden by the deepest laws of nature. If you could build a warp bubble from ordinary, positive energy, the kind that exists everywhere, in every star and every atom, then the whole project shifted from impossible in principle to merely difficult in practice. And difficult in practice is the kind of problem that human ingenuity has solved again and again throughout history. The shift was not from hard to easy. It was from forbidden to allowed, and that is a far more important boundary to cross. These new designs came at a price, of course. Most of them only allowed travel slower than light, at least in their first forms. But that was almost beside the point. The breakthrough was conceptual. For the first time, physicists had shown that you could create a genuine warp bubble, a region of reshaped space carrying a ship along inside it without needing the impossible. A real, physical structure that bent space to move a craft, built only from the kind of matter and energy we already understand. The dream had moved one enormous step closer to reality. The conversation shifted from, "Is this even possible?" to, "How do we make it go faster, and how do we build it?" This is a more profound shift than it might first appear. When a question moves from whether something can be done to how it can be done, the entire character of the inquiry changes. The first kind of question is about the laws of nature, about what reality permits. The second kind is about ingenuity, about what clever minds and patient effort can achieve within those laws. The first is a wall. The second is a road, however long and difficult. For decades, Faster-than-light travel had stood firmly on the wrong side of that line, treated as a question of basic possibility, answered with a flat no. The warp drive, refined and improved over the years, dragged it across to the other side, transforming it into a question of engineering and resources. That does not make it easy. The road remains immensely long. But a long road is a fundamentally different thing from an impassable wall. And recognizing the difference is itself a kind of progress. Some of these models drew on the idea of a shell of ordinary matter, carefully arranged, that could create a stable pocket of flat space inside a curved exterior. The ship would sit safely in the calm interior, while the structured shell around it did the work of warping space. It was less like a science fiction engine, glowing with mysterious power, and more like a precisely engineered configuration of mass, sculpting the geometry of space around itself. This shift in thinking was profound. For a long time, the warp drive had been imagined as a kind of magic, an exotic engine running on impossible fuel, almost supernatural in its operation. The newer designs reframed it as something far more grounded, a problem of arranging real matter and real energy in exactly the right pattern. The warp effect would emerge not from some mysterious force, but from the simple, if extraordinarily demanding, act of placing mass and energy in a precise three-dimensional structure. In a sense, the warp drive began to look less like a fantasy device and more like an architectural challenge, a question of building the right shape out of the right materials, even if those materials and that shape lay far beyond our present reach. The dream had been pulled, inch by inch, out of the realm of the impossible and into the realm of the merely extraordinarily difficult. Other researchers explored what they called physical warp drives, solutions grounded entirely in known physics, where the warp effect emerged from realistic distributions of energy. These were not perfect. They did not yet promise faster-than-light travel in a practical form, but they proved a vital point. The warp bubble was not inherently dependent on impossible ingredients. It was a real geometric structure that could, in principle, be constructed from real stuff. For decades, the assumption had been that the strange and possibly forbidden negative energy was an unavoidable part of any warp design, woven so deeply into the mathematics that it could never be removed. Showing that this was not necessarily so changed the entire landscape of the problem. It meant that the warp bubble belonged to the same family of objects as stars and planets and everything else in the physical universe, structures built from ordinary matter and ordinary energy, obeying ordinary rules. It was not a creature of some exotic and unreachable physics. It was a configuration of the same stuff that makes up everything we know, simply arranged in an extraordinarily precise and demanding way. That realization moved the warp drive a crucial step closer to the world of the real and the buildable, even if the building itself remained far beyond our present means. And that changed everything about how seriously the idea could be taken. There is a quiet but important detail worth pausing on here. When we talk about these designs, we are not talking about working machines sitting in a laboratory. We are talking about solutions to equations, configurations of space and energy that are mathematically consistent and physically allowed, but which remain far, far beyond our ability to construct. The energies involved, even in the most optimized designs, are still vastly greater than anything humanity can currently produce. We are not on the verge of launching a warp ship next year, or next decade, or possibly even next century. But that is not the point. It would be a mistake and a disservice to leave you with the impression that engineers are quietly assembling a starship in some hidden laboratory. Nothing of the sort is happening, and anyone who tells you otherwise is selling a fantasy. The gap between what the equations permit and what we can actually do remains vast. perhaps the vastest gap between theory and practice in all of science. We are, at best, at the very beginning of understanding whether this is possible, let alone how to achieve it. But the value of the work done so far is not that it brings a warp ship within immediate reach. Its value is that it has kept a door open that everyone assumed was sealed, and it has shown, again and again, that the reasons for declaring warp travel impossible were weaker than they first appeared. Each obstacle that once seemed final has, on closer inspection, turned out to be a challenge rather than a verdict. The point is that the door, once thought to be sealed shut by the iron laws of physics, has been shown to be open. The question has transformed from "could this ever be possible?" into "how far away is it and what would it take?" And in science, that shift in the question is everything. To appreciate just how significant this is, it helps to understand what a working warp drive would actually mean for our place in the universe. But the warp drive is not the only path that physicists have explored in their search for a way around the cosmic speed limit. Over the decades, several other strange and beautiful ideas have surfaced, each one a different attempt to outwit the tyranny of distance. Perhaps the most famous of these is the wormhole, an idea that springs once again from the equations of general relativity. If space can be bent and curved, then in principle it can be bent so severely that two distant points are brought close together, connected by a kind of tunnel through the fabric of reality. Imagine the universe as a vast sheet of paper, with two distant points marked on opposite ends. Normally, to travel between them, you would have to cross the entire length of the paper. But what if you folded the paper over, bringing those 2 points until they almost touched, and then punched a tiny tunnel between them? Suddenly, a journey that would have taken thousands of years across the surface could be completed in a single step through the tunnel. This is the essence of a wormhole, a shortcut that does not require traveling faster than light at all, but simply takes a different and far shorter route through curved space. The idea has a long and respectable history in physics. It emerged, like so much else, from the equations of general relativity, when physicists studying the mathematics of black holes noticed that the solutions seemed to describe not just a region from which nothing could escape, but a strange tunnel connecting one part of spacetime to another. For a long time, these tunnels were treated as mathematical oddities, curiosities with no real connection to the physical world. But as the decades passed, a handful of physicists began to take them seriously, asking whether, in principle, such a tunnel could be made traversable, whether a ship could actually pass through and emerge unharmed on the other side, in some distant corner of the cosmos. The vision is breathtaking. A network of wormholes could, in theory, connect distant regions of the galaxy like doorways in a vast cosmic house, allowing travelers to step from one star system to another without ever crossing the immense gulf of ordinary space between them. You would never exceed the speed of light along the path you traveled. You would simply travel a much shorter path than anyone watching from the outside would expect. The mathematics permits such structures to exist, and they have been studied seriously for decades. But wormholes come with their own brutal difficulties. The greatest of these is stability. A natural wormhole, even if one could somehow form, would be expected to collapse almost instantly, pinching itself shut before anything could pass through. To hold a wormhole open long enough to travel through it, you would need, once again, that strange and elusive exotic matter, the negative energy that resists the natural tendency of the tunnel to seal itself. And you would need it in vast quantities, threaded through the throat of the wormhole, propping it open against the relentless pull of its own collapse. So the wormhole, like the warp drive in its earliest form, runs headlong into the same fundamental obstacle. It demands a kind of matter we are not sure we can ever produce at scale. Still, the very fact that the equations allow such a thing keeps the dream alive. Another door standing slightly ajar in the architecture of physics. Then there is an idea even stranger than the wormhole, a hypothetical particle that has captured the imagination of physicists for generations. It is called the tachyon, and it represents perhaps the boldest interpretation of the speed limit of all. Remember that to accelerate an ordinary object up to the speed of light requires infinite energy, which is why nothing with mass can ever reach it. But what if there existed a particle that had always traveled faster than light, that had never been slower and never could be? For such a particle, the speed of light would not be a ceiling to be approached from below, but a floor that it could never sink down to. These hypothetical particles, the tachyons, would live their entire existence on the far side of the light barrier, in a realm where the everyday rules seem turned inside out. For a tachyon, slowing down would require more and more energy, and reaching the speed of light would demand the infinite energy that ordinary particles need to speed up to it. It is a mirror image of our familiar world, a reflection on the other side of the cosmic boundary. Picture the speed of light as a great river dividing reality into two shores. On our shore live all the ordinary things, the planets and stars and people, everything that moves slower than light, forever forbidden from crossing to the far bank. On the opposite shore, if it exists at all, would live the tachyons, things that have never touched our side and never could, eternally racing faster than light, unable to slow down across the river to join us. Two worlds, separated by a barrier neither can cross, each invisible and unreachable to the other. It is a strange and almost poetic vision, a universe split cleanly in two by the speed of light, with us trapped on the slow side, gazing across at a realm we can never enter. The trouble is that despite decades of searching, no one has ever found the slightest evidence that tachyons actually exist. They remain a possibility allowed by certain equations, but with no foothold in the real world that we have been able to detect. And worse, if they did exist and could be used to send signals, they would unleash the same nightmare of causality that haunts all faster-than-light schemes, the possibility of effects preceding their causes, of messages sent into the past. For these reasons, most physicists regard tachyons as a mathematical curiosity rather than a serious path to the stars. But they serve as a reminder of just how rich and strange the landscape of possibility becomes once you start questioning the absolute nature of the speed limit. There is yet another phenomenon that often gets tangled up in conversations about faster-than-light travel, and it deserves careful attention because it is both real and frequently misunderstood. It is called quantum entanglement, and it is one of the most genuinely bizarre features of reality that science has ever uncovered. When two particles become entangled, they form a connection so deep that measuring one instantly tells you something about the other, no matter how far apart they are. You could separate two entangled particles by the entire width of the galaxy, and the moment you measure one, the state of the other is instantly determined. At first glance, this sounds exactly like the faster-than-light communication we have been dreaming of. It seems as though information is leaping across the cosmos in an instant, with no regard for the speed of light whatsoever. Einstein himself was deeply troubled by this, famously describing it as spooky action at a distance, a phenomenon so strange that he suspected the theory must be incomplete. For years, this remained a philosophical puzzle, a debate about whether the strange connection was real or whether some hidden mechanism was secretly coordinating the particles all along. But over the past few decades, physicists have performed ever more refined and ingenious experiments to settle the question once and for all. They separated entangled particles across ever greater distances, across laboratories, across cities, even between the ground and satellites in orbit. And every time, the strange connection held. The particles behaved as a single linked system, no matter how far apart they were, their fates bound together in a way that defies any ordinary notion of separation. The experiments confirmed, beyond reasonable doubt, that the connection is genuine, that the universe really does weave these invisible threads between distant particles. Einstein's discomfort, it turned out, pointed not to a flaw in the theory, but to a feature of reality stranger than even he was willing to accept. But here is the subtle catch that closes the door. While the connection between entangled particles is genuinely instantaneous, it cannot be used to send any actual message. The outcome of measuring an entangled particle is random. You cannot choose what result you will get, and so you cannot encode any information into it. When you measure your particle and discover its state, you learn what the distant particle's state must be. But the person holding that distant particle sees only a random result, with no way to know that anything has happened at all until you send them a normal message, traveling no faster than light, to compare notes. The mysterious connection is real, but it carries no usable information across the gap. The cosmic censor, it seems, has anticipated this loophole and quietly sealed it. Entanglement is a profound and beautiful feature of reality, but it is not a telephone to the stars. It reminds us that nature guards its speed limit with remarkable cleverness, closing one apparent loophole after another, leaving only the deepest and most difficult one of all, the bending of space itself, still standing open. And so we return to the warp drive, which remains. Of all these ideas, the one that has survived the most scrutiny while keeping its promise intact. Now we can ask what a working warp drive would actually mean for our place in the universe. Right now, we are effectively trapped. Our entire species lives on a single small planet, orbiting a single ordinary star in the outer regions of one galaxy among hundreds of billions. Every human who has ever lived, every story, every dream, every triumph and tragedy has unfolded within a cosmic neighborhood so small it barely registers on the map of the cosmos. Think of the whole sweep of human history. Every empire that ever rose and fell, every work of art ever created, every word ever spoken in every language, every life ever lived from the first stirrings of our ancestors to this very moment, all of it has happened on the surface of one small planet. We have never set foot beyond our own moon. The most distant any human being has ever traveled is a journey of a few days to a barren rock hanging just beyond our atmosphere. Compared to the scale of the galaxy, we have not even left our own doorstep. We are like a people who have lived their entire existence in a single room, never once stepping outside, gazing through the window at an endless landscape we have no way to reach. The stars beckon, but they are impossibly far away. With our current technology, even the nearest star is a journey of thousands of years. We can send tiny robotic probes, but they would take tens of thousands of years to reach another star, long after the people who launched them are forgotten. A warp drive would shatter these limits. If you could travel even 10 times faster than light, the nearest star would be only months away. The center of our galaxy, 26,000 light-years distant, would become reachable within a human lifetime. If you could go 100 or 1,000 times faster than light, the entire galaxy would open up before us. 100,000 light-years of stars and worlds suddenly within reach. Try to imagine what that would do to the human story. A journey to a neighboring star, once a multi-generational ordeal lasting thousands of years, would become something closer to a long sea voyage of old, a matter of months, undertaken and survived by the same people who began it. Explorers could set out, reach an alien world, walk upon its surface, and return home to tell the tale, all within a single career. Trade and communication between star systems, unthinkable today, would become merely difficult rather than impossible. The galaxy, that vast and silent ocean of stars, would shrink in our imagination from an infinite wilderness into a charted territory, dotted with destinations we could actually reach. We would become, for the first time, a truly spacefaring species, no longer bound to a single world but free to roam among the stars. The cosmos would transform from an unreachable backdrop into a frontier to be explored. Think for a moment about what that would actually feel like. To live in a universe where the stars were genuinely within reach. Every clear night, you would look up and see not an untouchable painting, but a map of places you could go. The bright star low on the horizon would no longer be a distant abstraction, but a destination. A system with its own planets, its own possibilities, perhaps only a few months of travel away. Humanity would no longer be confined to a single fragile world, vulnerable to any disaster that might befall it. We could spread outward, establishing homes around other stars, weaving a web of human presence across the spiral arms of the galaxy. No longer would the fate of our entire species rest on the survival of one small planet. A single catastrophe, whether a wandering asteroid, a nearby stellar explosion, or some calamity of our own making, could no longer end the human story in a single stroke. We would be spread across many worlds, resilient, no longer all of us gathered in one fragile place. The entire character of our existence would change. We would go from being a single point of light, alone and isolated in the dark, to becoming a truly cosmic species, with the whole galaxy as our neighborhood. And there is something even more profound, buried in the way a warp drive works. Remember that inside the bubble, the ship experiences no acceleration and no strange effects of relativity. This matters more than it might first appear. When you travel close to the speed of light through normal space, time slows down for you, relative to everyone you left behind. If you flew to a distant star and back at nearly light speed, you might experience only a few years, while centuries passed on Earth. You would return to a world where everyone you knew was long gone. This is one of the most heartbreaking consequences of traveling close to the speed of light through ordinary space. A traveler who set out to explore a distant star and returned might experience only a few years of life aboard their ship. But on Earth, centuries would have rolled by. The friends they left behind would have grown old and gone. The world they returned to would be unrecognizable. Its language shifted, its cities transformed. Its memory of the traveler faded into history. They would arrive home as a stranger in their own world, a living relic of a time that everyone else had long since left behind. For all its wonder, this kind of travel comes at a terrible cost, severing the traveler from everyone and everything they ever loved. To journey to the stars this way would be to say goodbye forever, not just to a place, but to an entire age. This is the tragedy of relativistic travel. The faster you go, the more out of step you become with the home you left. But a warp drive sidesteps this entirely. Because the ship sits in its own calm bubble of flat space, time inside the bubble ticks along at a normal rate. In principle, a warp traveler could journey to a distant star and return, and find that roughly the same amount of time had passed both for them and for the people back home. You could explore the galaxy and still come back to the world you knew. This is a difference that cannot be overstated. The cruelest aspect of ordinary near-light speed travel is the way it isolates the traveler, severing them from their own time, condemning them to return as a stranger to a world that has moved on without them. The warp drive lifts this curse. Because the ship rests in its own calm bubble where time flows normally, the traveler does not fall out of step with the rest of humanity. A daughter could set out to explore a distant star and return to find her parents only a little older, her friends still her friends, her world still recognizably her own. The galaxy could be explored not at the cost of everything one loves, but while keeping those connections intact. This transforms the dream from a lonely, one-way exile into something far warmer, a genuine expansion of human reach that does not demand the sacrifice of human bonds. This is what makes the warp drive such a powerful dream. It does not just promise speed. It promises connection, the possibility of a galaxy where distant worlds are not separated by unbridgeable gulfs of time. This raises a haunting question that has troubled scientists for generations. If faster-than-light travel is possible, even in principle, then where is everyone else? Our galaxy is ancient, far older than our sun, filled with hundreds of billions of stars, many of them surrounded by worlds far older than the Earth. If even a handful of those worlds gave rise to intelligent life, and if even one of those civilizations discovered how to bend space and cross the galaxy, then they would have had countless ages to spread from star to star. A single civilization with the ability to travel faster than light could, in principle, visit every corner of the galaxy in a span of time that is brief compared to the age of the cosmos. By rights, the galaxy should be teeming with the signs of others, with ships and signals and the lingering traces of ancient visitors. And yet, when we look out into the silent dark, we see nothing. No ships, no signals, no unmistakable signs that anyone else is out there at all. We listen, and the cosmos offers back only an immense and patient quiet. This puzzle is sometimes called the Great Silence, and it has many possible answers, each one carrying its own weight. Perhaps intelligent life is far rarer than we hope, and we are alone, or nearly so. Perhaps civilizations tend to fade away before they ever master interstellar travel. Or perhaps, most soberingly of all, faster-than-light travel is simply impossible in practice, forever locked behind obstacles too great for anyone to overcome, no matter how clever they become. The silence of the sky might be telling us something profound about the warp drive, a warning written across the heavens that the door we think we have found may never truly open, or it might be telling us something else entirely. Perhaps the warp drive is possible, but every civilization that might have built one was simply too far away in space or time for its traces to reach us yet. Perhaps such civilizations exist right now, threading their way between distant stars while we sit in a quiet backwater of the galaxy, having only just begun to suspect that the journey is even conceivable. The silence could mean that the door is closed, or it could mean only that we are early, that we have arrived at the threshold of this discovery before anyone has had the chance to walk through it within our view. We cannot yet tell these possibilities apart. Or it might mean nothing at all, a puzzle whose answer is still hidden from us. We cannot yet say. But every time we contemplate the possibility of bending space to cross the stars, that silence hangs in the background, a quiet and unsettling companion to our boldest dreams. Of course, there are still enormous problems standing between the elegant mathematics and any real machine. Some of these problems are so deep that we do not yet know if they can ever be solved. One of them concerns how you would actually steer such a bubble. If the ship sits inside a region of flat space, completely isolated from the outside universe, how does it communicate with the outside to change course or stop? The very thing that protects the ship, its isolated bubble, might also make it impossible to control once the journey begins. This is a deeper problem than it first appears. To create the warp bubble in the first place, you would need to arrange exotic configurations of energy throughout the region of space the ship occupies. But once the bubble is moving faster than light, the central region of the ship cannot send any signal forward to the leading edge of the bubble. Nothing inside can outrun the bubble itself. This means that, in the simplest designs, the ship cannot give instructions to the very front of its own warp field while in flight. It would be like trying to steer a car whose steering wheel becomes disconnected the moment you press the accelerator. The entire journey, its speed, its direction, even the moment it ends, might have to be set in advance, programmed into the structure of the bubble before departure, with no way to change course once underway. Some physicists have wondered whether this makes practical warp travel fundamentally unworkable, while others suspect that cleverer designs might find a way around the difficulty. The honest answer is that we do not yet know. Then there is the question of what happens when the bubble forms and when it dissolves. Some calculations suggest that switching a warp bubble on or off could release bursts of energy and radiation, potentially intense enough to be dangerous to whatever lies ahead of the ship. This is a sobering possibility. The very process of creating and collapsing the warp field, of reshaping space so violently, might unleash floods of energy in the process. Imagine arriving at a peaceful, perhaps inhabited world, only for the act of stopping your ship to bathe the destination in a burst of lethal radiation. The warp drive, meant to be a tool of exploration and connection, might carry within it the seeds of destruction, a weapon disguised as a vessel. These are the kinds of concerns that emerge only when you take the idea seriously and follow the mathematics into its darker corners. A device powerful enough to bend space itself is, almost by definition, a device of immense and potentially dangerous power. Whether these effects are unavoidable or whether clever design could tame them remains an open and important question. There are even darker possibilities. As the ship races forward, its bubble might sweep up particles of dust and stray bits of matter from space, gathering them at the leading edge. When the bubble finally switched off at the destination, all of that collected matter could be released in a single, violent flash. It is a chilling thought. The same bubble that carries the ship so peacefully across the cosmos might be silently accumulating a deadly cargo along the way, particle by particle, all the dust and debris it sweeps from its path, piling up at the leading edge. And at journey's end, when the warp field finally dissolves, all of that accumulated energy could be unleashed at once, blasting forward toward whatever lies ahead. A warp ship arriving at a new world might announce itself not with a gentle landing, but with a devastating burst of high-energy particles, a consequence not of any weapon, but simply of the way the bubble gathers matter as it travels. Whether this danger is fundamental or merely a feature of particular designs is yet another question without a clear answer. These are not minor engineering details. They are profound questions about whether such a thing could ever be made safe, and we are nowhere near answering them. There is also the deeper issue of causality, one of the most troubling consequences of faster-than-light travel of any kind. In Einstein's universe, the speed of light is intimately tied to the order of cause and effect. It is the reason that causes always come before their effects, that you cannot influence the past. When you allow anything to travel faster than light, you begin to tangle the threads of cause and effect in alarming ways. To see why, you have to understand a strange consequence of relativity. Observers moving at different speeds do not always agree on the order in which two distant events happen. For events linked by ordinary cause and effect, this disagreement never causes trouble, because the speed of light guarantees that everyone agrees on which event came first. As long as nothing outruns light, cause always precedes effect for every possible observer, and the universe stays logically consistent. But the moment something travels faster than light, that guarantee evaporates. Different observers can now disagree about which event happened first, even when one supposedly caused the other. By chaining together faster-than-light journeys made by observers moving in different ways, you can, on paper, construct a route that arrives before it ever set out. Under certain conditions, faster-than-light travel can, at least on paper, be combined to create paths that loop back in time. The implications are dizzying and unsettling. If you could send something back to influence its own past, you open the door to paradoxes that seem to defy logic itself. The classic example is unsettling in its simplicity. If you could send a message, or an object, or yourself, backward in time, you could in principle interfere with the very events that led to your sending it in the first place. You could prevent your own journey from ever beginning, which would mean you never traveled back, which would mean nothing was prevented, which would mean you did travel back, in an endless logical knot with no resolution. These are not idle word games. They are genuine contradictions that emerge naturally from the mathematics, the moment faster-than-light travel is allowed in certain forms. And the universe, as far as we can tell, does not tolerate contradictions. It is this very intolerance that leads many physicists to suspect that some deep principle must protect the consistency of reality, either by forbidding faster-than-light travel entirely, or by arranging the universe so that such paradoxes can never actually occur. Physicists are deeply divided on what this means. Some believe the universe has built-in protections that prevent such paradoxes from ever occurring, mechanisms we do not yet understand that would forbid the dangerous loops while still allowing the journey. Others suspect that these paradoxes are a sign that faster-than-light travel, in any form, is ultimately forbidden by some deeper law we have not yet discovered. This is the frontier where our knowledge runs out and genuine mystery begins. We have equations that permit warp travel. We have designs that remove some of the worst obstacles. But we do not yet have a complete theory that ties everything together, that reconciles the bending of space with the quantum nature of reality, and tells us definitively whether the stars are truly within our reach. This is perhaps the deepest gap of all. We have two magnificent theories that describe the universe. One is general relativity, which governs the large-scale world of space, time, gravity, and the bending of the cosmos. The other is quantum physics, which governs the tiny world of particles and the restless energy of the vacuum. Each is extraordinarily successful in its own domain, but the two have never been fully reconciled. They speak different languages, and at the extreme conditions where both must apply at once, they break down into contradiction. The warp drive sits exactly at this troubled intersection. It demands the bending of space described by relativity, and it may demand the exotic vacuum energies described by quantum physics. And to fully understand whether it can work, we would need a theory that unites both. Such a theory, often called a theory of quantum gravity, remains the great unfinished work of modern physics, pursued by some of the finest minds of our age and still beyond our grasp. That complete theory, a full marriage of gravity and quantum physics, remains one of the greatest unsolved problems in all of science. And it may be that the final verdict on warp travel waits inside that undiscovered theory, locked away until we are clever enough to find it. It is worth pausing to imagine what it would actually take to build such a thing, even setting aside the staggering energy requirements for a moment. A real warp drive would be unlike any machine ever conceived. It would not be an engine in any familiar sense, with moving parts and burning fuel and exhaust streaming out behind it. It would be a device whose entire purpose was to sculpt the geometry of space itself, to impose a precise and exotic pattern of curvature on the region around the ship. To do this, you would need to control energy and matter with a precision and on a scale that dwarfs anything in our current capabilities. You would need to arrange that energy into an exact configuration, a shell or a structure surrounding the vessel, generating the compression in front and the expansion behind, and holding that pattern perfectly stable as the ship hurtled across the cosmos. The slightest imperfection might cause the whole delicate structure to collapse, or to tear itself apart, or to behave in ways no one could predict. We are talking about engineering, not merely on the scale of planets, but engineering the fabric of reality with surgical exactness. Nothing in our present technology comes remotely close. We cannot generate the necessary energies. We cannot shape space-time to order. We cannot even produce the exotic ingredients that some designs still require in anything more than the faintest microscopic traces. By any honest measure, a working warp drive lies generations away at the very least, and possibly far beyond that, if it is achievable at all. And yet, there have been moments when the dream brushed against the real world, when small groups of researchers tried to take the first tentative steps toward testing these ideas in a laboratory. In recent years, certain teams of physicists and engineers have proposed experiments aimed at detecting the faintest possible signatures of warped space. The idea was not to build a starship, of course, but to look for any measurable distortion in the geometry of space produced by carefully arranged energy fields. If even the tiniest, most minuscule warping of space could be detected in a laboratory, it would be a monumental proof of principle, a first whisper that the equations describe something real and reachable. Some of these efforts generated waves of excitement, and occasionally premature headlines announcing that a warp bubble had been created or detected. In nearly every case, the reality was far more modest. What was being measured, if anything, were effects so small and so easily confused with ordinary disturbances that no firm conclusion could be drawn. The history of this field is littered with bold announcements that quietly faded under closer scrutiny, with claimed effects that turned out to have mundane explanations, with hopes that outran the evidence. This is not a mark of failure. It is how science works, at the very edge of the possible, where the signal is faint, the stakes are high, and the temptation to see what we wish to see is always lurking. The honest physicists working in this area are the first to caution against overexcitement. They know that extraordinary claims demand extraordinary evidence, and that no such evidence has yet appeared. What they have produced instead is something quieter but more durable. A steadily growing body of theoretical work showing that the idea is not forbidden, that the obstacles, while immense, are not necessarily infinite, and that the question deserves serious and continued study. That, in itself, is a remarkable thing. A century ago, the very notion would have been laughed out of any respectable physics department. Today, it occupies a small but genuine corner of legitimate science, pursued by serious people using the most rigorous tools we have. The journey from fantasy to hypothesis is one of the most difficult journeys any idea can make, and the warp drive has, against all odds, completed it. Whether it can make the far harder journey from hypothesis to reality remains the great open question. So where does that leave us, standing here today, looking up at a sky full of stars we long to visit? It leaves us in a remarkable and unfamiliar position. For most of human history, the idea of traveling faster than light belonged entirely to fantasy. It was a storyteller's trick, a convenient way to move characters between worlds without dwelling on the impossible distances. No serious scientist would have staked their reputation on it. But something has shifted. Over the past few decades, faster-than-light travel has migrated, slowly and quietly, from the realm of pure fiction into the realm of legitimate, if highly speculative, science. It is studied in universities. It appears in respected journals. It is debated at conferences by physicists with serious credentials. This transformation, from pure fantasy to legitimate subject of study, is itself one of the most remarkable parts of the whole story. Ideas rarely make this journey. The graveyard of science is full of notions that sounded wonderful but turned out to violate some fundamental law, dismissed and forgotten. For an idea once confined entirely to the pages of fiction to climb its way into serious physics, to survive the scrutiny of skeptical experts, to earn a place in the real scientific literature, is extraordinarily rare. It does not happen because the idea is popular or because people wish it were true. It happens only when the mathematics holds up, when the concept refuses to be disproven, when serious examination keeps failing to find the fatal flaw. The warp drive has now withstood decades of such examination. It has been poked and prodded and challenged from every direction, and while the obstacles remain immense, the core idea has never been shown to be impossible. That endurance is what has earned it its strange and unlikely place in modern science. This does not mean it will ever work. The honest truth is that we simply do not know. The obstacles remain titanic, and any one of them could turn out to be a permanent, insurmountable barrier. The energy requirements, even in the most optimistic designs, remain far beyond anything we can produce or even clearly imagine producing. The questions of stability, of steering, of the dangerous bursts of radiation, of the deep threat to cause and effect, all of these stand unresolved. Any single one of them might prove fatal to the entire enterprise. It would be dishonest to pretend otherwise, to promise that warp travel is just around the corner, waiting for one more clever breakthrough. The truth is more humble and more uncertain than that. We have found that the door is not locked, but we have not yet found a way to open it, and we cannot be sure that we ever will. The path from here to a working warp drive, if such a path exists at all, is long, dark, and largely unmapped. We may walk it for generations and still not arrive, or we may discover, somewhere along the way, an obstacle so fundamental that it ends the journey for good. It is entirely possible that nature has hidden some final rule, some deep principle we have not yet uncovered, that forbids warp travel completely and forever. But it is also possible that it does not, and that possibility, however slim, is enough to keep the dream alive. History is full of things that were declared impossible right up until the moment someone did them. Respected scientists once calculated, with apparent rigor, that heavier-than-air flight could never work, that the very idea was a waste of serious thought. Brilliant minds dismissed the notion of reaching other worlds as childish fantasy. The list of confidently declared impossibilities that later became everyday reality is long and humbling. Each time, the mistake was the same. People confuse the limits of current technology with the limits of what nature allows. They saw that something could not be done with the tools of their day and concluded that it could never be done at all. But the laws of physics are one thing, and the temporary limits of our engineering are quite another. The warp drive may yet prove impossible, but if it does, it will be because nature truly forbids it, not merely because it is hard. And so far, nature has not said no. Powered flight was dismissed as a fool's errand by respected experts. Only a few years before, two brothers lifted off from a windy beach. The idea of splitting the atom, of reaching the moon, of holding the entire library of human knowledge in a device that fits in your pocket. All of these were once the stuff of dreams. The boundary between impossible and inevitable has a habit of moving. Consider how many times this has happened in our history. For thousands of years, the idea that human beings could fly was the very definition of impossible, a symbol of foolish ambition. And then, on a windswept stretch of sand, two bicycle makers lifted a fragile machine into the air for a handful of seconds, and the impossible became ordinary almost overnight. Within a single lifetime, We went from that first stumbling hop to crossing oceans in the air, and then to leaving the planet entirely. The same pattern repeated again and again. Reaching the moon was a fantasy of storytellers until the moment human boots pressed into its gray dust. Carrying the sum of human knowledge in a device small enough to slip into a pocket would have seemed like sorcery to people not so long ago. Time after time, the experts of one generation declare something forever beyond reach, only for the next generation to do it anyway. This does not mean every impossible thing will become possible. Some barriers are real and permanent. But it does mean we should be humble about declaring anything truly impossible, especially when the mathematics itself refuses to forbid it. What makes the warp drive so captivating is not the promise that it will definitely happen. It is the realization that it does not violate the laws of physics as we currently understand them. That single fact sets it apart from almost every other fantastical dream of travel and escape. Most impossible things are impossible because they collide head-on with some fundamental principle, some law that nature enforces without exception. The warp drive is different. It does not ask us to break any known law. It asks only that we find a way to do something extraordinarily difficult that the laws themselves permit. That is a profoundly different situation, and it is the reason the idea has survived where so many others have crumbled. It lives inside Einstein's own equations, the very theory that gave us the speed limit in the first place. The universe, it seems, wrote the rule against faster-than-light travel, and then, in the same breath, left us a hint that the rule might have an exception. There is a poetry to this that is hard to ignore. The same Einstein who showed us that nothing can be accelerated through space faster than light also gave us the theory of curved, flexible space that contains the warp drive within it. The hand that built the wall also, perhaps without realizing it, sketched the outline of a door. It is as though the universe, in laying down its great prohibition, could not quite bring itself to make that prohibition absolute, and so it left a single narrow path open, hidden in the geometry of space, waiting for someone clever enough to find it. Whether that path leads anywhere we can actually go remains the great unanswered question. But the mere existence of the path, written into the foundations of physics by the very theory that seemed to forbid the journey, is one of the most tantalizing facts in all of science. There is a deep beauty in that. For a century, we treated the speed of light as an unbreakable wall, a final boundary that nothing could cross. But the wall was never quite as solid as it appeared. We treated it as an unbroken barrier surrounding all of reality, sealing us inside a small region of accessible space. But it was never that. It was always a barrier around one particular kind of motion, leaving the rest of the cosmic landscape strangely open. The expanding universe already moves faster than light, carrying distant galaxies beyond our reach without breaking a single law. Space itself is the loophole, flexible and stretchable, indifferent to the limits placed on objects that merely move through it. There is a deep elegance in realizing this. The universe did not really forbid faster-than-light travel. It forbade one specific thing: the acceleration of objects through space beyond a certain speed. But it left the larger canvas, space itself, entirely free, able to stretch and warp without restriction. The cosmos demonstrated this freedom in the very first moments of its existence and continues to demonstrate it every day, as it carries the most distant galaxies away from us faster than any beam of light could chase them. The limit we thought was a fortress wall surrounding all possibility turns out to be a fence around a single field, with the whole rest of the landscape lying open beyond it. The challenge was never to break the rule. The challenge was to recognize that the rule was narrower than we believed, and then to find a way to exploit the vast freedom that lay just outside it. The whole challenge of the warp drive comes down to one staggering ambition: To take the same trick the universe used at the dawn of time, the bending and stretching of space itself, and to harness it, to control it, to bend it to our will. The universe performed this feat on a scale we can barely comprehend, reshaping space across the entire cosmos in the first instance of creation. What the warp drive asks is whether we can perform a tiny, controlled version of that same feat, not across the whole universe, but in a small bubble around a single ship. It is an audacity, almost beyond words, to take the most fundamental process of creation itself and tame it, to wield it deliberately, for our own purposes. We would be doing, on a minuscule and precise scale, what the cosmos once did with all its boundless power. It is, in a sense, the most audacious dream humanity has ever entertained. Not to travel through the cosmos, but to reshape the cosmos around us so that the journey becomes possible. And the most extraordinary thing of all is that, when you run the numbers, the universe does not say no. It says, not yet, and perhaps, and we shall see. That is a very different answer from the flat impossibility we once believed in. For a century, we read the verdict of physics as a simple and final refusal. The stars are unreachable. The speed of light is a wall. Accept your confinement and dream no further. But the deeper we looked, the more we realized that this verdict was a misreading. The universe never actually said the stars were forever beyond us. It said only that we could not reach them by the obvious route, by simply going faster and faster through space. About the other route, the reshaping of space itself, it remained silent, or rather, it offered a quiet and ambiguous encouragement, neither forbidding nor promising. And in that ambiguity lives all our hope. A flat no would have ended the conversation forever. A not yet, a perhaps, a we shall see, leaves the future open, and an open future is something humanity has always known how to work with. When you look up at the night sky tonight, take a moment to truly consider what you are seeing. Every point of light is a sun, and around many of those suns circle worlds we will never know. Worlds with oceans and storms and perhaps even life, separated from us by distances that have always seemed eternal. Some of those worlds may be barren and lifeless, scorched or frozen or airless. But others, surely, must be alive, draped in green and blue, washed by rains and warmed by their own suns, turning slowly beneath skies no human eye has ever seen. There may be forests there, and oceans teeming with creatures we cannot imagine, and perhaps, here and there, beings who look up at their own night sky and wonder, just as we do, whether anyone is looking back. The thought is almost unbearable in its mixture of wonder and longing. So much may be out there, so close in cosmic terms and yet so utterly beyond our grasp. For all of human history, those worlds have been forever beyond our reach, glittering and untouchable. Generation after generation has gazed up at the same scattered points of light, naming them, telling stories about them, longing to know what they truly are. Our ancestors saw gods and heroes in the patterns of the stars. We see suns, each one a furnace blazing across unimaginable distances, surrounded perhaps by worlds of their own. But for all that we have learned, the fundamental relationship has never changed. We look and we wonder, and we cannot go. The stars have always been the great symbol of the unreachable, the very measure of what lies forever beyond our grasp. To wish upon a star is to wish for something impossibly distant, something we never truly expect to attain. But somewhere in the quiet mathematics of curved space, in the patient work of physicists chasing an idea that refuses to die, a door has been found. It is a heavy door, and we do not yet know how to open it. We may not learn how for a very long time, if we ever learn at all. But it is there. For so much of human history, the stars represented the ultimate impossibility, the one frontier that even our boldest dreamers dared not seriously hope to cross. To stand here now, knowing that the laws of physics themselves do not absolutely forbid the journey, is to stand in a genuinely new moment. We are perhaps the first generation in all of human history to be able to say, with the backing of real science, that the road to the stars might exist. Not that we can travel it yet, not that we ever will, for certain, but that it might be there, written into the deep structure of reality, waiting. That knowledge alone is a kind of treasure, a shift in how we understand our own possibilities. And the simple knowledge that it exists changes how we look at the heavens. The stars are no longer entirely out of reach. They are merely far away, and far away is a problem to be solved. There is an enormous difference between those two ideas, and it is worth sitting with that difference for a moment. Something that is truly out of reach is a closed matter, a fact to be accepted and mourned, like the past we can never revisit. But something that is merely far away is an invitation, a challenge, a problem waiting for a solution. Humanity has always been at its best when facing problems of the second kind. We are not a species that accepts permanent limits gracefully. We probe them, test them, push against them, and time after time we discover that what looked like a wall was only a distance, and distances can be crossed. By moving the stars from the first category into the second, from the impossible into the merely difficult, the warp drive has done something profound to our relationship with the cosmos. It has turned the night sky from a closed door into an open question. And an open question, however hard, is the kind of thing our species was made to answer. We are the descendants of explorers who crossed oceans they could not see across, who climbed mountains they were told could not be climbed, who looked at the impossible and decided to try anyway. It is written into who we are. When our ancestors stood on the shore of an unknown sea, with no idea what lay beyond the horizon, something in them refused to accept that the water was the edge of the world. They built boats and sailed into the unknown, many never to return, until at last someone found the far shore. When mountains rose before them, they found ways over and through. When the sky itself seemed an impassable barrier, they built machines to conquer it, and then machines to leave the planet behind entirely. At every stage, there were those who said it could not be done, that some barriers were simply too great, that this was the final limit. And at every stage, the human refusal to accept those limits proved them wrong. The stars are the next horizon, the greatest and most daunting of all. For now, they remain beyond our reach. But if history teaches us anything, it is that beyond our reach is rarely the same as beyond our reach forever. Perhaps one day, our descendants will look back at this moment, this fragile beginning, when a forgotten idea crept out of science fiction and into the equations of reality, and they will recognize it for what it was. The moment we first dared to believe that the speed of light was not a wall, but a door. And the moment we began, ever so slowly, to search for the key, they will know whether the search succeeded or failed. They will know things we cannot, standing as we do at the very beginning, with so much still uncertain and unknown. But whatever they discover, this much will remain true. It was here, in our time, that the idea crossed over from fantasy into science. It was here that serious minds first showed that the laws of physics do not forbid the journey to the stars. And whether that journey is ever made, the simple act of proving it possible is a kind of achievement in itself, a widening of the horizon of what humanity is allowed to hope for. If this journey through the boundaries of the possible has filled you with wonder, be sure to like the video and subscribe so you never miss the next voyage into the mysteries of the cosmos. Because the universe is far stranger and far more generous with its secrets than we ever imagined. And, perhaps, hidden within its deepest equations, it has already left us the answer we have been searching for all along, waiting patiently for the moment we are finally ready to understand it.